Okay, so this is section 3.7, inverse functions. A lot of the stuff that we'll talk about today, we've already kind of accidentally talked about before. You just didn't know that we were talking about it, so you're welcome. So the first idea we want to examine here is like, I mean, if we have a physical machine that can run in one direction, like a car, can we then reverse it to go in the opposite direction, right? And so we're going to ask the same question about function machines, where you have some algebraic set of instructions that we put in an input and get a specific output. Well, can we reverse that process? And so to that end, we'll talk about Celsius and Fahrenheit conversions first. So, girl Betty going to a fashion show, she is in Milan. Over there, they use the Celsius, which makes no sense to any of us, obviously, because we use imperial units. But anyway, I digress. All of her temperature forecasts are in Celsius degrees. And I don't know about y'all, but I don't know if 26 degrees Celsius is comfortable or not. So we really want to get that into Fahrenheit. And so in order to do that, she's going to use this conversion formula. And so notice right here in this particular formula, we've actually got the Fahrenheit degrees as the input and the Celsius degrees as an output. So that's kind of a pain because then we're going to have to kind of plug things in and solve every single time. And as you can imagine, that's going to become quite tedious. And so, in this fictional scenario, she's like, oh man, wouldn't it be cool if I could input the Celsius and get the output of the Fahrenheit? And so again, this idea of reversing the direction of the conversion instead of like starting with Fahrenheit and converting to Celsius, we want to do the reverse. And so the idea of this is we can actually reverse this equation in the other direction by finding the inverse function. And so basically that's where the input of the original function becomes the output of the inverse function, and the output of the original function becomes the input of the inverse function. And so that sounds like word soup to me. And so that's fine. It's an idea that we've already examined when we looked at composition of functions, right? Remember, we're talking about this in terms of the input and the output to keep ourselves oriented so we don't get confused. So a little bit of notation first, because this is a language class every bit as it is a math class. And so given a function f of x, we're right here in the notes, we represent its inverse with this notation, read f inverse of x. And so the raised -1 is simply a part of the notation. It is not an exponent. It does not imply any power of -1. And so really importantly, f inverse of x does not mean 1 over f of x. Now, if you recall from Algebra 2, those negative exponents will drop something into the denominator. And while that is the place we draw this notation from, it is not always true. So f inverse of x does not mean this, because this is the reciprocal of the function f and not the inverse. And so again, as we discussed a second ago, the exponent-like notation comes exactly from the multiplicative identities and the multiplicative inverses, which are the reciprocals. But that is not always the case for all functions. So we abandon that and we use, again, I say all of that to say that that's not an exponent. That is notation that means inverse. And so again, the inverse undoes the regular function, and that's actually really handy. That's the basis of all of Algebra 1 is what is the inverse operation for addition, subtraction? What is the inverse operation for multiplication, division? And so this is not a new idea. We're just going to kick it up a notch. The next thing we're interested in doing is verifying a potential inverse is in fact the inverse for a given function. And so the way we do that is through composition of functions. So that's why it was so important for us to learn that. So basically, if I can compose a function together with its inverse, f inverse composed with f of x, and I obtain simply x, after simplifying that down, then the two functions are in fact inverses of one another. And, in fact, it will happen the other way too. So if you say f composed with f inverse of x, you'll actually obtain x if you obtained it the first time. And that's just because the two statements are what we call logically equivalent. And so, this will make more sense in just a second when I actually show it to you, but just to expose you to the kind of broad sweeping conceptual idea. So a few coordinate pairs from the graph of this function that I just kind of explained here, y equals 4x. So here are some coordinate pairs, some input-output pairs that are a part of this function's domain and range. And so its inverse, here are a few of those coordinate pairs. Now if you look, those coordinate pairs, x and y values, have just been interchanged. Again, going back to the original definition that I provided earlier, where I said that the input becomes the output and the output becomes the input. Well, that would make perfect sense that we were just switching x's and y's. Here is the really mathy definition if you'd like to revisit it. We really are more interested in a more practical definition, but there it is if you're a nerd like me. So example number 1, identifying an inverse function for any given input-output pair. And so we're saying, okay, if a particular one-to-one function, which by the way, that is important, we'll discuss why later, f of 2 is 4 and f of 5 is 12, what are the corresponding input and output values for the inverse? Well, if f of 2 is 4, then again, this idea of reversing the input and output for the inverse. F inverse of 4 is 2. And if f of 5 for the original function is 12, then reversing the inputs and outputs, then we have f inverse of 12 is 5. And there you go. That's literally it. Again, just showing that the input-output pairs are reversed for a particular function and its inverse. So next thing is what we'll actually do is testing an inverse algebraically. And this is where I was talking about where we're going to do f of g of x and g of f of x, one or the other, and determine if that simplifies to simply x. And if it does, then that's money because those are inverses. So let's see. Let's do some things here. So testing, if f of x is 1 over x plus 2 and g of x is 1 over x minus 2, is g the inverse of f? And so what we're going to do is, you can pick which way to go here. It doesn't really matter. You can choose. I'm just going to do f of g of x because just, that seems like, something I might want to do. So recall when we're composing functions, we want to just place g inside of f, 1 over x minus 2. Okay. So at this point, I'm just going to drop those parentheses because it's addition and it doesn't matter. And then we'll rewrite it. So negative 2 plus 2 is, clearly 0. So we have 1 over x. And so we have this fraction in a fraction business. And remember, when we're dividing fractions, we just want to multiply by the reciprocal. So this would end up being 1 times x over 1, which is clearly just x. And so, that is how we've shown because we composed f with g and obtained only x. So that means that g is, in fact, the inverse of f. Yes, it is. Okay. So you can do either one. It doesn't matter. If f of g of x yields only x, they are inverses. Or if it seems like it will be algebraically simpler to do g of f of x, then do that. It doesn't matter. We only need one. Example 3, determining inverse relationships for power functions. This is exactly the same question, but instead of with a rational, like we saw it a second ago, we are doing it with a cubic. So again, we'll do f of g of x. We'll compose f with g. This would be 1/3 x. All right, so for this, so when we're applying the powers here, this would be 1 over 9x cubed. So that's definitely not just x. And so no, they are not inverses. And so this is where you have to be really sure about your algebraic simplification skills, because it's a lot harder to say that it's not than it is, right? Because you know when to stop if it is. But here, I know that I can't do anything else with this. And so I'm stuck, because just like if one of them is, then it's an inverse. If one of them isn't, it's definitely not. So one will bust the whole thing wide open. So moving on to finding the domain and range of inverse functions. Once again, we are thinking about this idea very similar to when we composed functions and found the composite domain, that, the output of one function has to be the input of the other function. Therefore, the range of the original function must be exactly the domain of the other function, or else it's not going to work. We're going to have like holes and gaps and stuff, and we can't do that. It is possible to not have an inverse function. All functions do not have inverses. Some very special functions can have a restricted domain and then have an inverse. And so one of the really important things to know about an inverse function, and this is a lot of words, and I'm going to condense this down for you. You're welcome to go back and read it, is we can restrict a function to a part of domain on which it is one-to-one, because we need a function to be one-to-one in order for it to have an inverse. Because think about it. The definition of a function means that I don't have any repeating inputs for different outputs. And so if I were to flip that around and the range and the domain flip, then it's got to be one-to-one, because there can be no multiple input and output pairs that are repeating on either side. And so, this is just redundant. The range of the function f is the domain of the inverse of f, blah, 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 word soup. And so here's your how-to. If I give you a function, find the domain and range of its inverse. And so basically what has to happen here is if the function is already one-to-one, write the range of the original function as the domain of the inverse, and that's a done deal, right? Because it's already one-to-one, and so there are no domain restrictions that have to take place to make this work. We know some one-to-one functions. The cubic and the linear function are one-to-one automatically. We know this from our study of toolkit functions earlier in the unit. But we got a couple, especially that quadratic, the x squared, that is going to throw us for a loop. And if you guys took pre-cal with me and you remember trig, you remember that we had to restrict the sine and cosine function to a very small domain that was strictly non-decreasing in order to make that one-to-one, in order to construct the arc sine and the arc cosine function, or the cosine inverse and sine inverse. And so maybe that's ringing a bell for us. So in example number 4, let's look at the inverses of the toolkit functions. Basically, there are only a few of these that are not one-to-one, right? This one is not one-to-one, if you remember. This one is not, and this guy is not. So we're going to examine those. And then also the absolute value is not one-to-one. So let's look. Constant function, not one-to-one. There is no domain except one point on which it could be one-to-one, so it has no inverse. So that's out the window. Absolute value, we know what that looks like. We just studied that in the last section that you did on Wednesday. So it looks like that. And so remember, for a function to be one-to-one, it's got to pass the horizontal line test. So if I just restrict it to that domain and cut out the rest, boom, all of a sudden passes the horizontal line test and is a one-to-one function, because it is strictly increasing. There is no place where it changes direction. Therefore, there are no chance for any of those input outputs to repeat. This reciprocal squared function can also be restricted. So just taking a look at these down here. So again, not one-to-one currently, but if we restrict it to this domain, not a problem. Also, this absolute value, the reciprocal square can be restricted to here and be one-to-one, or doesn't matter. You can do it over here too. Whichever one you choose, it's up to you. As long as you only choose one and get rid of the other. So again, the trick is to make it pass the horizontal line test, because, we can just do what we want here, as long as we follow the rules. So again, finding and evaluating inverse functions. So once we have a one-to-one, we can evaluate that inverse at specific inputs. Or we can even construct a complete representation of the inverse in a lot of cases, using all the way back to freshman geometry. So interpreting the inverse of a tabular function, all this means is a fancy word for it is in a table. So I got this table. I plug in the minutes and it gives me the miles. Super complex, right? So let's interpret f inverse of 70. And so all that really means is I'm asking the question for the function f, what is the input that will give me an output of 70? Right? Because, f inverse of 70, the inverse takes the output of the original function as the input. So this is actually the question I want to know, which is so simple. We've done this a trillion times, and y'all are really good at it. So what input gives me an output of 70? Well, that's 90. It's just the corresponding input to the output 70 of the original function. That's that. So given the graph, okay, this is not a problem either because we know how to evaluate a function normally using a graph. And now we just go backwards. That's all the inverse does, is takes us backwards. So first find g of 3. So input 3 gives us output 1. So g of 3 is simply 1. And then, go in the other direction. G inverse of 3 says that for this graph, the output is 3. What is the corresponding input? So here is output 3. Corresponding input is 5. And that's that. We just go backwards. That's all. Seems difficult, but isn't. Finding inverses of functions represented by formulas. Hey, we've already done these. This is not a big deal. So it's just got a fancy name now. So we're back to our Celsius and Fahrenheit conversion. Find a formula for the inverse function that gives Fahrenheit temperature as a function of Celsius temperature. Okay, I literally just want to solve for F. This is not that scary. So we'll just multiply both sides by 9 over 5, which is, equivalent to multiplying both sides or dividing both sides by 5/9, but whatever. I'm not using a calculator, and we need to know that those things are algebraically equivalent anyway. Okay, and so then we'll add 32 to both sides, so 9 over 5c plus 32 equals F. And there is the inverse function. Where instead of going from Fahrenheit to an output of Celsius, we're now going to an output of Fahrenheit from an input of Celsius. Okay, solving to find an inverse function. This one's a rational function. This is not a big deal. So we're just going to say y equals 2 over x minus 3 plus 4. All right, so we're going to swap the input and output. That just means that this is going to be an x now, and this is going to be a y now. And I'm going to solve for y. Again, not a big deal. So the first thing we need to do is we need to get this 4 to the other side. So x minus 4 equals 2y minus 3 on the bottom. So remember, if we have a rational like this, we want to multiply to get rid of the denominator. So I'm going to draw an arrow over here so we can save some space. All right. Yep. So this is x minus 4. That's a y, Kim. 4 times y minus 3. And so now let's just, multiply it out. So this will be xy minus 3x minus 4y plus 12 equals 2. So at this point, it's probably helpful for you to remind yourself actually what you're doing here. We're solving for y. And so if you don't keep that in mind, if you don't know where you're going, you're not going to get there. So we're trying to solve for y. So let's just kind of visually remind ourselves of that. Okay. So if I'm solving for y, I need everything that isn't y to go to the other side of the equation. So let's do that. So we're saying 3x, and then 2 minus 12 is minus 10. Now see, I'm in the unique position now where I can factor that y out. So I have x minus 4 equals 3x minus 10. And then I can just divide by everything that isn't y because, the miracles of high school algebra. And so nothing will simplify further here. And this is really where I want to be. So there's your inverse function. And so this is actually f inverse of x, aka y. So that's going to follow that same procedure. We've seen that a little bit already. Okay, so find the inverse of the function f of x equals 2 plus root quantity x minus 4. And so again, we'll start with y equals 2 plus root x minus 4. And then we'll say, switch the input and output because that's what an inverse does. Okay, so x minus 2 equals root y minus 4. Okie dokie. So we're going to have to square this to get rid of the root. And, we should recognize that this is about to cause a problem. Because this inverse is not 1-to-1, right? Because we got that square there. So we're going to have to deal with that. So let's go ahead and finish solving for y. So this is x minus 2 squared plus 4 equals y. Okay, so let's get a handle on what the range of this function is, because we're going to have to restrict that so that the domain of the original function fits. because we can't have like not allowed inputs, because remember, we have to be 1-to-1. We have to go back and forth for each input-output pair without an issue. And we know that if there is a negative under this, then that is going to be a problem, right? So we can examine one or both. We can examine this guy and make it 1-to-1, or we can examine this and make sure that the domain is appropriate for everything under there. So, I mean, it's going to give you kind of the same idea. So let's use toolkit functions and our knowledge of what those look like and transformations, since we just did that. So this is a quadratic, starts at, vertex is usually 0, 0. We're going to go left 4, and then we're going to, no. What in the world? Oops. No, we're not. We're going to go up 4, and then we're going to right 2. So this will be up 4, and then we're going to right 2, and our vertex is going to be here now. So what do I need to do to restrict this to the appropriate domain so that the range works out? Well, we need to make this 1-to-1. So let's go here. Okay. So I know that this has to be 1-to-1. And so this is going to have to be a domain of 2 to positive infinity. But remember that the range of this function must be the domain of this function. So let's really take a look here at what's happening. What's the range of this function? It's going to be 4 and up, right? So it's never going to go below that. And let's examine this. What's going to have to happen over here in order to make this workable? So the domain of this original function has to match the range. So let's make sure that that's happening. Let's make sure that that's happening. So we know from before that the radicand has to be greater than or equal to 0, right? So x actually has to be greater than or equal to 4. Okay, so now I've confirmed here. The domain of this function is equivalent to the range of this function, where y is greater than or equal to 4. See how those two match? So this is going to have a restriction. And this is the restriction we're talking about. We've got to make it to where this particular function can only have outputs that fit the domain of this function. All right. So from there, we're almost done finding an inverse function using the entire constructed graph. So we can find the inverse of this function, but we need to know what the entire graph looks like. And so basically what we need to know here is that, lost my train of thought. I was thinking about something else. Sorry. You're probably thinking about something else by now too, because this is a really long one. Sorry about that. Just had to be that way. So the bottom line is that if we are switching input and output pairs, graphically what that looks like is a reflection over the identity line y equals x. And so what that looks like is you actually just switch the input and output pairs, right? So 1, 1 becomes 1, 1. This point is going to be 2, 4, and so it's going to be 4, 2. So that'd be way over here. So you're going to end up with something that looks just like this, which makes sense because if this is the restricted x squared, we know its inverse is the square root of x. But you do have like this restricted domain, so you only have the function that exists greater than 0. The bottom line to do that, if we want to construct that, I mean, we're just going to reflect this guy right over this identity line. Right, and so that'll be here. And if this is a point 4, 2, it's going to become 2, 4. And if this is a point, oh no, that's it right there. If that is 0, negative 4, then this is going to become negative 4, 0. And so now we've got this lovely sketch of what this guy should look like. And it is a perfect reflection over the identity y equals x. So we know that's bingo. See, There it is right there. And so now you have some problem sets. Probably what we'll focus on Tuesday when I get back is working through some of these problems. So I'll probably pick some difficult problems since I'm not going to be there Monday either. I'll be back Tuesday for office hours. So I think what I'm going to do instead of, moving on, I think we've done enough, is I'm going to pick some of the more difficult problems from the 3 lectures from this week, and we're gonna work some of those out. So if there's one in specific that you would like to see, send it to me by the end of the day tomorrow on Remind, and I'll make sure to include it, especially the ones that seem to be causing people the most problems. And then, we're going to take some time to play cleanup, and I'll answer questions. So I don't want you to panic about me like giving you a test on Wednesday. I'm not doing that. All right. So I hope you have a wonderful, wonderful weekend. Thanks for hanging in for this super long lecture, and I will see you guys on Tuesday.